It looked like fish lines.
I thought God was getting back on me. When I was in college, I would be then going to be so I do. I spent the last 18 years of my career in chemistry. I learned all this crazy stuff, organic chemistry, and all these things of fractional distillation. And I never cared about.
I looked at it.
Suddenly, I God got me that good on that. That's a crazy balls. After 50 years, I finally trained to it. So I think, I love this. I said that to some guys, and he says, I want to train. Okay. Yeah. Yeah, we'll take here's the area we'll go on. You got this slide on. I didn't know it right there. What you do? Then we get together, and then we get the one piece more. So yeah. Yeah, right, yeah. All right, good. All right. Okay, we're 50 seconds short of 10:30, so we'll start this whole roll. Welcome to Spaceport Aircraft Hub. The session hosts are going to be giving us. The rules are we're going to talk for 25 minutes, 5 minutes for questions, and we'll probably go in right? So those are hard numbers we have. Questions, when the questions come up, please feel free to ask them. Try to keep it short and distinct so you can they have a woman about. I'm Rick Wills, I'm one of the judges, and is back. He's also so without further ado, it's 10:30. You're on.
Awesome. Hello, everybody. My name is Lucas. So SOAR is the Students' Organization for Aerospace Research at the University of Calgary in Canada. And this year we are in the 10K SRAN hybrid category. So what we're going to be talking about is kind of the high-level development process of our new hybrid motor. We're flying for the first time at a competition here this year. So to put this kind of into context, as a bit of team history, the motor that we are building off of is also a hybrid motor known as Atlantis 2. This was developed back for the 2019 competition. And this was kind of after COVID, we came back and we started developing the next hybrid for Periscope. So a couple things about this motor. You'll notice the specific impulse and characteristic velocity that's relatively low for nitrous oxide and paraffin propellants. So there was a lot of room for improvement to get more out of the same form factor of motor and same flow rates. It had about 2.5 kilonewtons of peak thrust, which isn't fantastic for the kind of rockets we're trying to do here. So we wanted to bump that up as well. It also experienced fuel sloughing rather regularly. Those of you that are familiar with hybrids, fuel sloughing is basically when chunks of the fuel get entrained into the flow such that they do not combust completely before exiting the chamber. Obviously, that results in a lot of lost performance, so that's something that we sought to improve upon. Even beyond the fuel sloughing, though, there was not that good of mixing in Atlantis 2. As you can see by the brightness of the plume, there's still a lot of combustion going on outside of the chamber. Okay, so that basically brings us to our starting point for Paris 1, which is our objectives. So we wanted to increase the reliability because Atlantis 2 also had sort of reliability metrics at times. We wanted to improve upon that. We wanted to increase that combustion efficiency, decrease those fuel sloughing events, and increase the average thrust output to about 4.5 kilonewtons, which our sim was saying would get us a good rocket that would fly to 10 or potentially 30K in the future with some modifications. And so the first thing that we wanted to address was reliability. We used to have a big issue with our igniters where we have very variable ignition time, burn times, which is obviously not ideal if, for example, you want to do igniters using line of sight. So one of the things that we tried to address was the ignition time. So we ended up switching to an igniter design that had a nichrome heating element, pretty common, but we had a center bore that contained smokeless powder, which would be our initiator, and then rocket candy to carry on burn. We also found out through a series of tests that the igniters tended to kind of explode without any kind of relief holes we eventually added to let out the smoke and prevent it from blowing up. We open our main engine valve using a automated main engine valve open. The igniters we characterized for their ignition time, and over a series of tests and 45 igniters, we found an average ignition delay of 1.8 seconds with a standard deviation of 0.4. To kind of put that into context, that's a confidence interval of at least 95. The burn time is on average 4.3 seconds. So we set our actuation delay to 3.5 seconds, and a single igniter that we have tested to date has ever been outside of this kind of ignition. Okay, so now that we've had an igniter and had a reliable means of starting our motor, we can start tackling some of the other challenges of Atlantis 2. First up, combustion efficiency. So there's a couple of ways to tackle combustion efficiency, and to kind of put it in perspective, I'll talk a bit about how just that works in hybrids in general. So in hybrids, you'll have your solid fuel and you'll have your liquid oxidizer flowing in the middle. What will happen is that you get a oxidizer-rich zone and a fuel-rich zone. In order to burn completely, you need to mix those two. In order to mix those two, there's a couple different ways of doing it. One, simply just giving it more time to mix, allow the fusion to occur. However, the fusion is a rather slow process compared to the rather high speeds we're seeing in the chamber. Not quite sonic, but quite high, like 1.3 or something like that. So another way that has been found in literature to work quite well is to have a passive mixing device. Very simple, basically, it just redirects the flow in such a way that the two streams are forced to combine, and they can then react before passing through the muscle. And this might not seem like a big deal, but literature shows that this can yield significant performance improvements. These figures are taken from a research paper published from research at the University of Calgary. Basically, what was done here was a hybrid motor was taken and fired for a baseline, that's the black. And then the only thing that was changed on this motor was the addition of a mixing plate. And then what happened was the combustion efficiency increased dramatically, and you can see that on the thrust as well as the chamber pressure. Both are significantly higher just with this passive mixing process. So in terms of implementation, there's a couple ways of doing this. We are pretty lucky that we have a short burn, so we have a lot of flexibility in our material selection. We were able to get away with simply using material that has enough heat capacity to survive the burn, and obviously you can't take steady state combustion, but we don't need it. So we just selected a steel-based material. And to reduce the heat transfer a little bit, prolong that lifetime, we have a refractory ceramic coating that's typically used for this coating is kind of the gate to my property. So we needed quite the QA process to make sure that things work. Before we got that down, we had some failures of the mixing devices. But now that we have that down, we've had reliable tests with 4 static fires out of Paris 1 and 1 flight about a month ago.
The final thing that we was wanting to address is our fuel sloughing. So one of the issues with paraffin, for those of you that are not familiar, it is a liquefied fuel, which without extra mechanical strength, it can essentially eject out of the motor without being burned, which you kind of saw in that heating motor. So the way that we kind of addressed this was to use a 3D printed matrix and cast our paraffin into this matrix. So the matrix would be giving it mechanical strength, while also kind of reducing your compression across the board. The way that we kind of did this was we generated a unit cell that we propagate to a cylindrical geometry with our center bore under there. So there's a couple different ways that this can be addressed. We needed essentially a triply periodic structure, meaning it can repeat in all 3 directions, so you can change to any geometry that you like for your combustion chamber. It also needs to have 0 enclosed volume, so you don't essentially create a bunch of pockets of air inside your bubble. And ideally, it would also be tunable to your desired compression rate in some form. And as I said earlier, it would be able to fit a cylindrical geometry. So we ended up going with a gyroid midsole. Not any particular reason other than the fact that it's a simple formula and it meets all the criteria. We would generate this matrix in MATLAB and 3D print it, and then cast our paraffin into it. So the benefits of this, again, you're able to retain our paraffin fuel. The matrix is super easy to generate, and we could retain our spin casting manufacturing method, which works really well for us in the past.
Okay, so now that we kind of had figured out how we're actually going to tackle these improvements that we intended, we had to figure out how to actually go and put that in the motor. So much of the motor is similar to the old Atlantis 2 design, but some important changes. So at the head end here, we have our injector bulkhead. You'll notice it's a modular design. So we have a sealing bulkhead using redundant O-ring, a tension ring that just houses O-rings, and it is a lot easier to insert. Clearance is a little different, so that we can install it very easily. So we don't have to fight the O-rings, basically. Inside the injector bulkhead, we have a smooth board for our transfer fitting that allows our plumbing to not over constrain the tank. So our plumbing is actually able to move about 50 thousandths of an inch back if need be from cooling during the burn. And then we have our injector plate. We retained the simple shower head from Atlantis 2 motor because we're able to get very good efficiency with that. We didn't see a need to increase the complexity there. Then after our pre-chamber, we have our custom fuel, and then we have our post-chamber with our passive mixing device. And after that, we have our nozzle, conical graphite nozzle, retained in a aluminum 6061 lens. This entire fuel drain is encased in a phenolic liner, and this phenolic liner is installed in the aluminum combustion chamber.
So, as we put together our designs, we looked obviously validated on this. So we began with steel chamberless, essentially to reduce the need to worry about mechanical failure and combustion itself, so that we can validate our filters and pieces separately. Basically, from Calgary, we took a pipeline piece, welded some flanges on it, and we're able to test that on our test. After this, we conducted a flight hardware test, which validated our actual flight chamber and flight components. And then back in September, we did a certification certifier to be able to certify our motor to launch at CAR events, which are Canadian Association of Rocketry events, which is basically the ability to launch a bit locally, not have to competitions to test our rocket motors. And finally, about a month ago, Ouroboros did its maiden flight to 15,000 feet out in Taber, Alberta. For those of you that don't know, that's on the Vancouver side of Canada. And we were able to recover mostly successfully, and our motor burned quite well.
Okay, so with all these things implemented, I'll talk a little bit about actually what kind of performance increase we saw. So the characteristic velocity, which is loosely speaking a measure of combustion efficiency, increased by 74%. The specific impulse increased by 60.7%. The thrust increased a lot more. That's not 100% representative because we did increase our flow rate slightly. But nevertheless, we got more thrust. And once again, we are very, very happy to be the first ever CAR JCF, which is the Canadian equivalent of Tripoli, basically, certified experimental motor in Canada. So we're now actually able to launch locally. We're the only student team in Canada to be able to do that with this thrust curve is from our very first qualification side fire of Paris 1 in our steel chamber. This will actually also rather inconveniently set our test site on fire, but it's okay. No one was hurt, nothing was damaged. We were able to put the grass fire out. Well, the fire department was. But nevertheless, you'll see one thing that we really are quite proud of is the start of our burn doesn't have a very, very large peak that you'll see in a lot of hybrids. So the thrust curve is rather flat, which allows us to design our airframe with a slightly lower safety factor so that we have higher mass efficiency overall. This again just puts some perspective visually compared to Atlantis 2, and you can see increase in specific impulse as well as characteristic velocity. For context, we are operating at the same Atlantis, just the flow rates in play.
And finally, for some of our future work, as we mentioned earlier, Ouroboros and Paris 1 are designed to be the baseline for future hybrid development at UFC after a pause was taken. I won't give too much away, so hopefully we can come back and present this in a few years, but one of the things that we want to target is an optimal OF ratio. So for those of you that are familiar with hybrids, you know about the OF shift that occurs during the current. One of the nice things about using matrix to cast your paradigm in is that we can tune the regression using the infill percentage. So we're looking at a way to try and achieve an ideal OF for the entire with this state panel. And the next thing we want to target is superior combustion efficiency. And although we saw a lot of increase into our mixing device, we never really addressed sort of the location and some of the finer details of it. So to interact to expand our quality capabilities and we'll have there.
That's all. If you guys have any questions, feel free.
You guys mentioned that with 3D printing the matrix stabilize your fluid. What materials are you using to print it out?
We tested a couple different things. Right now, we're using Nucleus.
What going back to your mixing plate? how did you determine the right hole size and thickness and position where, what part of the chamber was it optimal? How do you optimize it?
It's a good question. So the hole size we kept consistent from the paper that we used to develop this concept. And basically, it is the open area of the mixing plate is 3 times the throat area of the nozzle to make sure that we keep the flow nice and slow for the mixing plate, basically. And the sorry, what was your other question?
The
location.
diameter in the center. How do you optimize that?
Yes. So the hub diameter is smaller than the nozzle throat for safety. So the mixing plate is actually designed to fail such that the hub gets ejected, and it does so safely.
And you use steel. Is it supposed to be steel?
Yes.
Which grade?
Just mild steel, 1016.
Mild steel.
Yeah.
Okay.
As for the location, again, we based it off of the literature that we got this concept from. But what we did was we essentially scaled it to our motor using the diameter and length of the closed chamber.
How do you retain?
So we have EPDM insulation on the inside of our phenolic casing. And basically what we do is we have an outside layer that goes between the phenolic and the mixing plate. And then we have a secondary layer that goes in before the mixing plate that's smaller than the outer diameter of the mixing plate. And then the mixing plate goes in and then another piece goes in on the outside. It's mechanically retained. We also use structural epoxy, but we don't depend on the structural epoxy to actually survive the burn.
Going back to the paraffin wax with the matrix and the when you go through the regression of the program, did you encounter any sort of unexpected inconsistencies or any sort of strange things that came up when you tried to material like that?
Surprisingly less than you would think. It doesn't seem to change like the overall combustion behavior significantly, but it does have an effect, obviously, just not the regression. Yeah.
How can you guys explain your motor burnout a little bit more? I saw the sort of transition into gas, but you also benefit as well.
Yeah, we're not actually at our test site. We aerospace with the aerospace laboratory. We're not allowed for safety reasons to go to vapor. So essentially, we overfill our we shut off valve or whatever. Or our flight data is actually done with vapor.
Did you see any issues with combustion instability?
Yeah, that's a good question. Yeah, we're definitely still seeing some instabilities. We saw that in our flight as well. I'm not 100% sure if it's just sloughing still, because we were able to minimize sloughing, not eliminate entirely, or if it is actually just instability. Literature does suggest that you have to be careful adding these mixing devices. They are prone to exciting those instabilities, but further work is required to properly yeah.
Does the fatigue life of the passive mixing device a concern or so?
We haven't seen any issues with that yet. We don't use further. Yeah.
What additives do you put in your paraffin?
We use different opacifiers. We've experimented with different ones. Anything from tar to graphite to carbon black.
On your testing, did you do any sort of measurement of the resistance of those wires, or is that something?
That's part of the manufacturing process. Is we correctly control the resistance of the actual micropieces.
So those are all fairly new.
Yeah. We keep them all ideally within 0.1 PS.
For your injectors, are you using commercial ones or
in-house? Anyone else?
Questions? Let's give a round of applause for Alex. Please be careful exiting the door. Don't want to stampede.
Yeah, they do like burgers. Okay, that helped me do a lot of practice. Yeah, like on the schedule, I'm not looking forward to get excited about certain things. I gotta say that. I like the fact that I don't have to
Could you actually say it?
Oh, these kind of venues.
Yeah.
Yeah. So I guess.
Thanks, man.
Gotcha.
Tell us. Yeah, I know. And I gave him the wrong answer. But why would you? It's told us. You know what? I don't know. I think Scott was okay. Like like a barbecue. We've got a bar. Yeah. So the university in town. It's in town, so you can take transit. Okay. Or nine counties. Okay. All right. But yeah, it's say like down south, they got that test. What?